Welcome to lesson 4 in this module, which looks at the structure of atoms and periodic properties. And the topic of this lesson is the Schrodinger or quantum mechanical atomic model. Now, this is essentially a review of what we did in our last lecture and completing what we had started in that lecture. Now, in the previous podcast, we basically introduced the idea of a wave function, that the electron is traveling with a wave function, and that the wave function as a sine function describes the particular wave-like motion of an electron within a confined region of space. And we looked at the particle in a box, or the electron confined to a one-dimensional box, and showed what the wave function is, and showed that the wave function basically is dependent on the principal quantum number n, and in fact the wave function changes with respect to n and has different values of energy. Essentially what we pointed out as well is that because of the fact that the electron is traveling as a wave function, or has a wave function traveling as a wave, there is an uncertainty with determining exactly where the electron is for a specific wave function, or for a wave traveling with a specific wave function. And so this idea of a wave function, even though it is particularly useful in allowing us to be able to understand the wave motion of the electron, it captures the idea of the Heisenberg uncertainty principle, which basically states that you cannot simultaneously determine with any precision the momentum and position of the electron with any great degree of at the same time, more or less. Now, so moving from the particle in a one-dimensional box, or the electron in a one-dimensional box, we can extend this idea of the electron moving with its wave function in 3 dimensions. And here we have, for a particular principal quantum number n equal 1 in this case, that there is an associated wave function. In this case, the wave function is has the lowest value possible. Now, if we were to consider the fact that the wave function really essentially is a 3-dimensional a description of the 3-dimensional movement, or the movement of the electron in 3 dimensions, then one can envisage that the wave function, or we can envision the wave function looking like this, spreading out in 3 dimensions, or in all dimensions for the most part. And this basically shows us how uncertain it is that that we can actually identify exactly where the electron is if it's traveling with a particular wave function. Now, just to pinpoint that the way how the wave function looks in 3 dimensions is pretty much the way how it looks in 1 dimension. Clearly, except that it's moving in 3 dimensions. Now, what we're showing here is that is a depiction of essentially the 3-dimensional movement of the wave function. The concentric circles basically shows that the wave function is spreading out in 3 dimensions, and it's essentially similar to what you would observe if you were to drop an object into a bath of water. You would see the waves basically spreading out in 3 dimensions in concentric circles. This basically sums up the idea of the wave function essentially. Remember that we're considering as well that the electron, the wave motion of the electron is that described as a standing wave for the most part. Now, when n is equal to 2, we see that for the electron in a one-dimensional box, the wave function basically shows one wavelength of the wave motion. And if we were to depict that as a 3-dimensional wave function, we see that it essentially attains the same shape, but it's just spread out in 3 dimensions. And again, here is a depiction of the 3-dimensional movement of the wave function. Now, clearly, as shown from the electron in the one-dimensional box, we see that the wave function has a positive value and a negative value. And this is basically showing the same thing, where we have a positive wave function and then a negative wave function. Now, I show this to show or to state that because of the three-dimensional wave motion, or the fact that the wave function is spread out over 3 dimensions, shows why the electron's position is so uncertain. And we're going to essentially see how well, we're going to basically utilize this, or accept this idea of the uncertainty of identifying the position of the electron as it is moving around the nucleus. Now, the wave function basically shows the wave-like motion of the electron in 3 dimensions, but the wave function has an associated value of energy. And the Schrodinger wave equation basically shows us the solution or the determination of the wave function, and linking that with or solving it with respect to the energy that the electron will have as it is traveling within that confined region or confined boundary. And the Schrodinger wave equation is shown here, where it incorporates the kinetic energy with respect to the wave function, and the potential energy with respect to the wave function, to give you the total energy of the electron and its total and the wave function, essentially. This is a simplified wave function where H represents the energy terms here. It's called a Hamiltonian, or an energy operator, and of course E is the total energy, or the energy function of the wave function. Now, what basically is important to take from this is that the wave function, as we've seen, based on the particle in a one-dimensional box, is quantized. That is to say that for different values of n equal 1, 2, 3, 4, and so on, the wave function changes, and also the corresponding energies change. And this is basically showing that the electron's motion, the electron properties, essentially, as determined by the wave function and the associated energy, are all quantized and as such have specific values. Okay? So the question then is, how do we move from showing the wave function or the wave motion as described by the wave function of the electron in a 3-dimensional box or a 3-dimensional space to a spherical atom, in this case a hydrogen atom? Or we can probably restate it as asking, how do we move from describing the electron location in a 3-dimensional box to describing it in the hydrogen atom? And so that's basically what we're going to be exploring in this lesson. We're going to be basically looking at the wave function, breaking down the wave function or into different components, particularly the what we describe as the radial component and the angular component, and using equations described by those components, or to describe those components, to basically give us an idea of how it is that the electron is moving within a region of space. We're going to introduce this idea of an orbital, because an orbital is essentially described as the region of space within which the electron is moving, and this region of space, or the orbital, is defined or described by the wave function. And we're going to essentially then look at how it is that we basically come up with the different types of orbitals or atomic orbitals as described or proposed by the Schrodinger solution of the wave function, and then identify the different kinds of orbitals by quantum numbers. We've met one, the principal quantum number, but we're going to introduce other quantum numbers which essentially define specifically what the wave function, what the orbital is, or how the orbitals basically are different. And then we're going to basically present mathematical or graphical descriptions of these wave functions, and basically have an idea of what it is saying, or what they're saying about the probability of finding the electron within a particular region of space. Now, in moving from the 3-dimensional box to a spherical atom, I basically have proposed this idea where we can consider the atom as the Earth, and the region of space, the atmosphere that is around the Earth, as the region of space where the electron is moving in. And we can basically use as the electron an airplane traveling in the region of space. And if we're going to be able to determine exactly where the airplane is uh, uh, in the skies, basically, we would have to have specific kinds of, we have to use specific parameters to basically describe exactly where that airplane is. Clearly, one would have to use the distance from the Earth, right, or the vertical distance from the Earth to the plane as one, and we can basically call that the radius if we're going to relate that to the electron. But of course, the radius can be the same at different parts in the sky or different locations of the electron around the nucleus. And so we would have to then use coordinates called spherical coordinates, which basically are angles with respect to specific axes. And in the case of the airplane, we can basically use lines of latitude and longitude, and we can equate that essentially to being the angles of theta and phi if we're looking at the electron moving around the nucleus. And so we have these three parameters that we use, the distance and two angles, theta and phi, to basically describe the relative position or the position of the electron relative to the XYZ axes essentially. And we see that if the electron is traveling with a specific wave function, then we would see that the wave function is dependent on these parameters, the distance r and the angles theta and phi. And as such, the wave function is essentially broken up or divided into two components, or in fact is the product of two components: the radial component, which is based on the distance r, or the radius, and the angular component y, which is dependent on the angles theta and phi. All right, and so because we're incorporating the radial component or a radial description of the location of the electron, and an angular component or description of the electron's location, then that effectively defines more or less the region of space around the nucleus where the electron is likely to be moving. And we call this region of space an orbital or an atomic orbital. And it basically turns out that different orbitals or different regions of space within which the electron is likely to be found give rise to different orbitals. And how is it that these orbitals are different from each other? They are different based on their sizes, their shapes, and their orientation. What are we talking about when we talk about size? We're talking about basically how large the orbital is, and the size and the size is basically speaking to how far the electron is from the nucleus, and clearly that is related to the principal quantum number n in this case, and we know that n also gives us an idea of the difference in energy that the electron has. And so if an electron is in an orbital that is close to the nucleus, then that orbital is a small orbital. And as the electron moves further away from the nucleus, the orbital becomes larger, the principal quantum number is increasing, and the energy is increasing. The shape speaks to the specific region of space that the electron is moving. Recognize that the electron has a 360 degrees space to move through. Of course, the electron will not necessarily, depending on the energy, depending on its wave function, will not necessarily all the time be located or likely to be located around the entire nucleus. It will likely to be in specific regions around the nucleus. And that specific region of space essentially defines the shape that the orbital will have in specific terms. And then, because we are talking about a three-dimensional system, we're talking about, well, we describe three-dimensional systems through the X, Y, Z planes, and planes or axes relative to those planes. Then the orbitals, or the particular region of space within which the electron can be found, is dependent on those planes as well. And that describes essentially the orientation of the orbital, in what direction or what angle, from the nucleus the electron is likely to be moving. Now, these different parameters or characteristics of the orbitals are defined through various quantum numbers. We are familiar with the principal quantum number, n, and the values that n is 1, 2, 3, 4, and so on. And as I said before, the principal quantum number basically defines or gives us an idea of the size and the energy of the orbital. And so as n is increasing, the electron is at a higher energy level further from the nucleus. We can basically go back to or utilize some of what we've understood from the Bohr atom or the Bohr model, where as n is increasing, the electron is at a larger distance from the nucleus, but each orbit that n describes is of a particular energy, and as the electron is moving to higher orbits, the electron becomes higher, the energy becomes higher and higher. Of course, we must make the distinction between this model, which is the Schrodinger quantum model, which speaks to orbitals, as opposed to orbits of the Bohr model. Okay, so we're not supposed to confuse either of them, but we can basically relate aspects of them for the most part. Then the other quantum number is the orbital angular momentum quantum number, and it's designated L, and it has values of 0, 1, 2, 3, up to n minus 1. And this orbital angular momentum quantum number basically describes the shape or the angular distribution of the orbital. And there are essentially 4 types of orbitals. Because we have only 4 values of L, 0, 1, 2, 3, and when it is an S, and when L is equal to 0, we have an S orbital. When L is equal to 1, we have a P orbital, 2, D orbital, 3, and F orbital. And then the other quantum number is the magnetic quantum number, denoted as ML, M subscript L I should say, which is equal to values of 0, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, up to plus or minus L. Alright, and this basically defines the orientation in space that the orbital might occupy, and the fact that the value of ML can be 0, plus or negative, indicates to us that these orbitals have different phases, recognizing that the orbital is defined through the wave function, and the wave function, as we had been introduced to it, basically has a plus phase, a negative phase, and it can also have a 0 value. Now, the magnetic quantum number basically allows us to determine the numbers of orbitals that are associated with a particular value of L, or a particular orbital. And the number of orbitals basically can be calculated through this relationship 2L plus 1. And we see that if, for example, L is equal to 3, right? L is equal to 3, 2 times 3 is 6 plus 1. There are 7 F orbitals. If 2L, if we're talking about L equals 2, then it's 2 times 2 plus 1, that is equal to 5. We have 5d orbitals. And if we look at, for example, this one, for example, 5d orbitals, the magnetic quantum number will have values of ml, which is equal to 0, plus 1, minus 1, plus 2, and minus 2. Alright, because L is 2, right? And so the ml can have a maximum value of a plus L or a plus 2, and a minimum value of a minus L or minus 2. And so in the case of L is equal to 2, or the d orbitals, the values of ml are 0, minus 1, plus 1, minus 2, and plus 2, and each of them represent one different orbital. So we have 5 different orbitals. And if we go back to here, where we calculate the number of orbitals, 2 times 2 plus 1, that is 5. That speaks to the 5 different orbitals, the 5 different d orbitals. And again, the plus and the negative indicate to us that they have different phases, and we'll see essentially what that essentially looks like later on. Now, understanding the relationship of quantum numbers and orbitals, or understanding how it is that we define orbitals through their quantum numbers, is very critical for us to be able to determining the electronic configuration of atoms. Alright? And so we're going to basically establish some relationships here. Now, if n is equal to 1, right, n is equal to 1, then L is equal to n minus 1, right? And if n is equal to 1, then n minus 1 is 0, and so the value of L is equal to 0, and that speaks to an s orbital. Okay? Now, what are the values of ml? ml is equal to 0 plus or minus L. Since L is equal to 0, then ml is only equal to 0. Alright? The total number of orbitals is 1, well, the number of orbitals, s orbitals, is 1, and for when n is equal to 1, the total number of orbitals is equal to 1. What happens when n is equal to 2? Alright, L, what is the value of L? L is equal to 0 and n minus 1. Since n is equal to 2, then 2 minus 1 is equal to 1, so there are two values of L, 0 and 1. That tells us that we have two different types of orbitals, s and s orbital, and a p orbital. Now, what are the values of ml? For the s orbital, we know that ml is equal to 0, but for the p orbital, ml is equal to 0 plus or minus L. Since L is equal to 1, then we're talking about minus 1 and plus 1. So we have three values of ml, minus 1, 0, and 1, which speaks to three different orbitals. Alright, now when n is equal to 2, we have a total of 4 orbitals, the 1s orbital and the 3 p orbitals. And when n is equal to 3, right, L is equal to 0, n minus 1, right, or n is equal to 0 up to n minus 1. Now, since n is equal to 3, then L is equal to the maximum value of L is basically equal to 3 minus 1, which is 2, and therefore the values of L is equal to 0, 1, and 2. 0, 1, and 2. Now, for the 0, we know that that's an s orbital, and ml is equal to 1, and there is only one s orbital. For when L is equal to 1, that's a p orbital. We know that there are three values of ml, minus 1, 0, and 1, and that's a total of 3 orbitals. But when we have L is equal to 2, that is the d orbital, and what are the ml values? ml is equal to 0 plus or minus L. Since L is equal to 2, then we're talking about maximum value of plus 2 and a minimum value of minus 2. Alright, so and then of course moving from minus through to 0 to the plus, and therefore for ml we have values of minus 1, values of minus 2, minus 2, minus 1, 0, 1, and 2, or values of a value of 0, a value of plus or minus 1, a value of plus or minus 2. And we see that there are 5 of these types of d orbitals. Alright, however, when n is equal to 3, we have 3 different types of orbitals: the s orbital, the p orbital, and the d orbitals, and there are a total of 9 orbitals. Now, since we are increasing in the value of n, it means that this s orbital here is of a lower energy than this s orbital and this p orbital, right? And since n is equal to 3, then this s orbital is of a higher energy than these three p orbitals and these 5d orbitals. And so we can basically rank the energies with respect to, or the orbitals rather, with respect to the principal quantum number and their associated energies as defined by the values of L. Alright, so in the case of n equals 1, we have a 1s, okay, right? N equals 2, we have a 2s and a 2p, or 3 2p's, alright? N is equal to 3, we have a 3s, 3p's, and 3d's. And that's basically what this basically is what this allowed us to be able to calculate. Now, one of the important things that we need to bear in mind is that because n basically indicates the energy of the orbitals, one can expect that for when n is equal to 2, the 2s and the 2p orbitals have the same energy. Alright, and the reason why we've drawn these lines, which basically essentially represent the different orbitals, we draw them side by side, we basically are referring to them as having the same energy, or describing them as being degenerate, right? Degeneracy is a term given to orbitals that have the same energy. And when n is equal to 3, we see that all the orbitals have the same quantum number, right? And principal quantum number, I should say, and they all have the same energy. Alright, they're all degenerate. Okay? Now, how do we represent these? So we know how to basically, we know the different types of atomic orbitals. We know how they are designated based on their quantum numbers. And we can have an idea of the energies that they have based on the principal quantum number. We know what the shape is, we know what their orientations are, for the most part, or likely to be. How do we represent these atomic orbitals, or how do we visually represent them, and how do we interpret them to allow us to be able to understand where the electron is likely to be found in the region of space defined by these orbitals? Well, we clearly have to go back to what the wave function tells us, and particularly by the two different components that the wave function have, the radial component and the angular component. Now, the wave function, as you will eventually, as we'll be showing here, and the components, the radial component and the angular component of the wave function, are essentially mathematical functions. And these mathematical functions are distinct or different based on the type of orbital that we have, or the types of, or the different wave functions that we have that define the different orbitals. Now, the mathematical functions are not for us to be able to decipher or determine at this level. These are very complicated mathematical functions to derive, but we can actually use them, however, and interpret them to get an idea of what the orbital look like, and what the orbitals tell us about determining exactly where the electron is around the nucleus. Now let us look at the 1s orbital and see what the wave function tells us about that particular orbital. 1s orbital, the 1s orbital is defined for the hydrogen atom, Z is equal to 1, right? Atomic number Z is equal to 1, and when N is equal to 1, right? L is equal to 0 and ML is equal to 0. We go back to our table here. That's basically what we did to define the 1s orbital. We looked at n is equal to 1. So we look at the values of n, l, and ml. Alright, and in this case we're looking at the 1s orbital because n is equal to 1, l is equal to 0, and ml is equal to 0. So what is the wave function? The wave function psi is equal to this term here, right? And it is determined through the radial component r and the angular component y. The radial component is given by this term here, and the angular component is given by this term here, and the product of both of them give us the overall wave function. Alright, what does this wave function tell us? Well, one can plot the wave function with respect to this value here, r. Notice that the value r, which is the radius, is shown in our wave function, and the r is also related to a0, which is the Bohr radius, which is 54 picometers, which is essentially the radius determined based on the Bohr model of which is hydrogen, the Bohr hydrogen atom. Now, when we look at the wave function, we see that there is an exponential term, however, in our equation, and that the exponential term is incumbent on the radius with respect to the Bohr radius. All right, and so if we were to plot a graph of wave function versus r, we essentially will get an exponential curve. Now, for those of us who don't understand what an exponential curve is, I would suggest that you go look at a mathematics book, and you can see essentially some examples of what exponential terms look like, or exponential curves look like. Alright, what is the significance? What is it that this wave function tells us, and how is it changing? How is it changing with respect to r? Alright, how is this exponential curve changing with respect to r? Well, the first thing that we should look at is the angular component. We see that the angular component is dependent on theta and phi, but we don't really see any angles per se in this equation. What we're seeing is pi, and again, from basic mathematics, pi essentially is a value that is related to 360 degrees, and so we're talking about a full circle. All right, so this wave function then is essentially speaking to the wave function that defines an electron within a region of 360 degrees. 360 degrees. All right. Now, we can also say that the angular wave function, because it's the square root of 1 over 4 pi, is independent of angles theta and phi. Alright? That's just saying it another way that we're really talking about a circle. Alright? And this is basically the case, and is the same for all s orbitals. Alright? S orbitals essentially are circular. That's basically what it's saying. Now, the wave function allows us to define the region of space within which we are likely to see the electron or find the electron, but the square of the wave function allows us to get a probability of finding where the electron is. Alright, and so when we square the wave function, when we square this wave function here, we get this new term. Alright, and if we were to plot psi squared versus r, we get a plot that looks like this. Right, so we have psi squared versus r, and if we also plot psi versus r, we get more or less a similar change in the wave function, or the wave function square. Now, what this is telling us is that and this is basically this is in fact a classical example of an exponential curve. All right, and in this case, for a 1s orbital, what we're seeing is that the wave function is a maximum at a value, at a radius of 0. Right, or right at the nucleus, if we were thinking about the electron in the atom, but it decreases exponentially. The probability, and we're looking specifically at probability here, the probability decreases exponentially as the radius increases. Alright, and it decreases to a value of 0 when you get past the Bohr radius. Alright, notice the radius here r over a naught. Okay, so if let's see. Alright, let's not say that. Right. So let me repeat. So the probability of finding the electron is maximum at the nucleus, and it decreases exponentially as r is increasing. And when you get beyond the Bohr radius, which is 54 picometers, the wave function basically becomes 0. That is to say that there is a specific region of space or boundary within which you will find or likely to find the electron. Okay? Oops, sorry. So looking at the wave function and the square of the wave function also gives us an idea of the energy of the electron. And this here is basically showing us that, again, close to the nucleus, alright, the wave function is maximum, the square of the wave function is maximum, the energy of the electron is maximum, but the energy also decreases exponentially as we move from the nucleus. Okay? So how do we give a pictorial representation of what that wave function and wave function square look like? Again, we can plot the probability density versus radius in two dimensions, that is through the xy, along the x-axis through the xy plane. Now remember that we said that the angular wave function is not dependent on angles theta and phi. We are speaking specifically of a region of space that is mapped out through 360 degrees Celsius. Sorry, 360 degrees. We're not talking about temperature here. 360 degrees. Now, if we were to plot that psi squared versus r, what we're seeing is that the wave function decreases exponentially from the nucleus, which is at a maximum, but decreases exponentially as we move from or get further from the nucleus. But what we see is that the wave function basically looks the same or has the same shape in all dimensions, and that is to say that this means that the 1s orbital, the s orbital, is spherically symmetrical, right? It has the same spherical symmetry throughout, and that is because the angular wave function is independent of theta and phi. If, for example, we are saying that along this axis here, the probability of finding the electron is a particular value, we're saying that along the same value on the y-axis, we will see that the probability is the same. And on the negative side of the x-axis and the negative side of the y-axis, at the same value along those axes, the probability is the same. Alright? So that speaks to its spherical symmetry. The probability is the same at a specific point along any given axis, at any particular angle around the nucleus. Alright? And so we basically can represent the 1s orbital in terms of a probability density, or the electron density around the nucleus. Here we have the center of the nucleus, and these dots basically are representing the probability distribution of the electrons around the nucleus. And so we see that at close to the nucleus it is very high, and the probability basically is decreasing as we are moving away from the nucleus out to a value which basically is equivalent to the Bohr radius of 54 picometers. Alright, if we go beyond that boundary or that value, remember that the wave function is defined by a boundary condition, then the probability decreases or is in fact zero, and you're not likely to find the electron. Again, look at the spherical symmetrical nature of the distribution on all sides around the nucleus. The probability is the same. Alright, and this is essentially what this contour map is representing. Again, at a 95% contour or a 95% probability of finding the electron probability decreases decreases exponentially as we move from the nucleus up to a particular boundary. Okay? What about the 2s orbital? For a 2s orbital, we can say we can probably relate to the helium atom. Z is equal to 2, and again n is equal to, actually this is supposed to be n is equal to 2, L is equal to 0, ML is equal to 0. One can envisage that the 2s orbital, because n is equal to 2, right? This is supposed to be n is equal to 2. The 2s orbital is a larger orbital than the 1s orbital, because one would expect that with an increase in quantum number, principal quantum number n, we're talking about a larger orbital or a larger region of space, and also the electron has a higher energy in that orbital. What is the wave function? The wave function is equal to r times y. This term here basically defines r, and this term here defines y. Again, y in the 2s orbital is the same as y in the 1s orbital, and the product of both basically give us this overall wave function. Now, the interesting thing about the 2s orbital is that the value of the wave function that defines a 2s orbital is controlled by this part of the equation. Alright? Why? Because r is changing. If r changes, then this term changes, and overall this term changes. Alright? So if, for example, r is a very, very small value, that is to say that it's very close to the nucleus, then this term here is a very small term. Alright? And so let's, for example, use an arbitrary value of 0.1. If r is 0.1 picometers from the nucleus, then 0.1 over 54 picometers is a very, very small value, and therefore 2 minus that value basically is approximately 2. And so we see that at a very small distance from the nucleus, or very close to the nucleus, the wave function, when we calculate the wave function, we see that the wave function is a maximum, okay, and it is a positive value. All right. So for small r values, r over a naught is smaller than 2, and for very small values of r, it is a maximum and it is a positive value. Now, as we are moving from the nucleus, that is to say that as r increases, this term becomes larger, and 2 minus a larger term means that overall this becomes a smaller term. And so as r is increasing, the wave function is decreasing. Alright, so we start out here where wave function is a maximum close to the nucleus, and as r is increasing, the wave function is decreasing exponentially, right? We have our exponential term. But it still remains positive up to a point, right? When r becomes equals to a naught, right? That is to say that a naught over a naught is equal to 1. We still have a positive value of our wave function. But when r increases to a naught, or 2 times a naught, I should say, then this becomes, this value here becomes 2. And therefore 2 minus 2 is equal to 0, and overall the wave function becomes equal to 0. That is when the wave function crosses or gets to the x-axis here, or the 0 line on the x-axis. Alright? Whenever the wave function is 0, we call that a node. If you go back to our particle in a box model, or standing wave, when the wave function crosses or actually either crosses that 0 line, or is at both ends of the box, it is called a node. All right, and clearly you can't square a zero value, so the probability or the electron density is going to be equal to 0 at that point. What happens when R increases further than greater than 2A naught? If R is equal to 3A naught, or 2.1A naught I should say, and then 2.2 and so on, it becomes negative because this term here is a larger term. Let's say that this term here now becomes 3. 2 minus 3 is equal to negative, and so the wave function now becomes negative. Alright? And it becomes negative to a minimum until we get to the Bohr radius, where it starts to become it actually tends back to 0 for the most part. What if we square that wave function, right? What if we square this wave function equation? We get this equation. We don't want to look at the equation per se. We want to look at, if we were to square the values that are used to create this graph, we see that this part, which is positive, remains positive, obviously, but it's a larger value. And the part that is negative, negative times a negative, becomes a positive. So and of course, where we see that there is 0, that remains 0. So we're seeing here that the wave function squared, or the probability density, or the probability of finding the electron decreases as we're moving away from the nucleus. It gets to a value of 0. We get to a region of space where the probability of finding the electron is 0. Then it starts to increase to a maximum, but it's not as maximum as before, and then starts to decrease. And pictorially, in our fuzzy ball, as we describe it, again, close to the nucleus, the probability of finding the electron is high. Again, because it's spherically symmetrical, the probability decreases exponentially in all directions to the same extent, but then gets to now a region where the probability of finding the electron is 0. We call that the node, and then it starts to increase to a maximum again, and then starts to decrease thereafter. And so this is a 2s orbital. The difference between a 2s orbital and a 1s orbital, two things, is that the 2s orbital is larger than a 1s orbital because principal quantum number n is equal to 2 in the 2s orbital, and principal quantum number n is equal to 1 in the 1s orbital. But also, for the 2s orbital, there is a region of 0 electron density, or 0 probability of finding the electron. But in the 1s orbital, that is not the case. We don't have a radial node as the case is in the 2s orbital. What about p orbitals? P orbitals, you can have values of, when you have p orbitals when L is equal to 1, and there are 3 values, or 3 types of p orbitals as defined by the different values of ml. Alright, so this table here is basically showing us what the wave functions are, both the angular wave function and the radial wave function. For the s orbitals, right, the wave function, the angular wave function is the same, but of course the radial wave functions differ depending on the value of n. In this case, 3s, 2s, 1s, they all have different values of r, basically indicating essentially that that the radial wave function changes based on the size of the principal quantum number n. Okay? Now, as it relates to the p orbitals, the angular wave functions are defined by these 3 equations here. And the radial wave function is defined again based on the value of n. Alright? Let us look at, say, for example, the 2p orbital. Alright? What we see is that we have 3, as I said before, 3 different angular values for the wave function. Remember, one would expect, in fact, that you would have three different p orbitals because ml is equal to -1, 0, and 1. We have three, and the numbers, sorry, the signs indicate that we have the orientation, right? Remember that ml basically gives us an idea of the orientation of the orbital. All right, this is telling us that the orientation of each orbital is different. All right, and so this is basically what this is saying to us. We have they differ based on these trigonometric functions. All right, we see that now for the angular wave function as opposed to the s orbital, there are values, sorry, of theta and phi, and the values of theta and phi are dependent on these trig functions, cosine, sine, and so on. Well, cosine and sine in this case. All right. Now, essentially, what this is telling us is that these values point along different axes. They point along the x-axis, the y-axis, and the z-axis. All right. Or in other words, the angular component of the wave function is different based or is dependent on the plane or the axis or the specific orientation. All right. Now, if we go back to the radial component of the wave function, we have only one value for the radial component for all three different types of three different types of p orbitals. If we look at the term, we see that when r is equal to 0, the p orbital vanishes. That is to say, this term here, this sigma term, that captures r, if r is equal to 0, then all of this becomes equal to 0. Alright? And this is different from what we saw with the s orbital. For the s orbital, when r is equal to 0, alright, the wave function is maximum. But we're seeing that if r is equal to 0, the radial component of the wave function becomes 0, right? Because this is 0, the exponential term becomes 0. And if you multiply r by y, we get 0, which gives us the overall wave function. All right? And so at the nucleus, in a p orbital, there are no electrons. All right? But that is different from the case where electrons are confined to an s orbital. We have electrons right at the nucleus. Now, how do we draw or represent our p orbitals pictorially? Let us look at the angular wave function. Remember that the radial wave function basically is not going to give us a whole lot. It's just that the size is going to be increasing because r is increasing. But the shape of the p orbital is going to now depend on the angles theta and phi. Alright? What are those? What is that shape? Let us look at this one, which is the pz orbital. The angular wave function is dependent on cos theta. Alright? And cos theta basically represents the z-axis. Now, so if we were to start off with our x, z axes, right? As theta is increasing, right? This angle here, theta, increases from the z-axis. So we're moving from the 0 z-axis to a positive value of the z-axis, positive value of theta, that is. So as theta is increasing, or rather, let us start out when theta is equal to 0. When theta is equal to 0, then cos 0 is equal to plus 1. So that tells us that the angular wave function basically is along the z-axis, and it is a maximum value along the z-axis. So the wave function is basically right here. Alright? And so when theta is increasing, the wave function now starts to decrease. Alright? And then when we get to a value of theta which is equal to 90, right, cos 90 is equal to 0. And so we end up where, along the x-axis, where the wave function becomes 0. Okay? And we call that an angular node, because it's an angular wave function. Okay? And an angular node represents 0 probability of finding the electron. Okay? So when theta increases, however, further, we see again that the wave function becomes negative. Okay? And then it becomes negative all the way up, and it becomes a minimum when we get to 180 degrees, right? So theta is equal to now 180 degrees, and cos theta is equal to -1. We now end up with an angular minimum. All right. So of course we can actually continue with the change in the theta. We see now that we end up with a situation where the wave function forms this dumbbell shape. Okay, where one side is positive and one side is negative, or we could basically call them two lobes, a positive lobe and a negative lobe. In the signs positive and negative are indicative of phases. If you go back to our wave function along within the particle in the box, or as a standing wave, we see that the wave function can have a positive value and a negative value and a 0 value again. All right. Now, what if we were to square the wave function? Well, the negative lobe and the negative lobe basically is going to give us an idea, a representation of the probability of finding the electron, and the positive lobe is also going to give us an idea of finding the electron. So if we were to, we have our, this is our z-axis here. We have our positive lobe and our negative lobe. If we were to square both lobes and represent it in 3 dimensions, we see that both lobes basically show equal probability of finding the electron. It's just that one is on the positive z-axis, or one is along the positive z-axis, and the other is along the negative z-axis. Of course, in between both lobes is along the xy plane. That is where we have 0 probability of finding the electron. Alright? So we have 0 probability along the xy plane. Then the probability increases to a maximum just outside of the nucleus. Going back to the 0 probability, remember that we said that at the nucleus there's 0 likelihood of finding the electron, which is different from that in an s orbital where the probability is maximum. Right? This is the opposite here, where in a p orbital the probability of finding the electron is 0, but as you move away from the nucleus it increases to a maximum and then decreases thereafter. Alright, and so this is basically how we represent in chemistry terms the orbitals, the p orbitals. We have one side here which is darker shaded and the other side is lighter shaded. The darker shade and the light shade basically indicate to us that we have 2 different phases, a positive phase and a negative phase, and we have the nodal plane in between. We have the nodal plane in between both lobes, which basically indicate to us that we have 0 probability of finding the electron. So here we have the 3 different p orbitals. We have the px orbital, the py, and the pz, basically showing us that for the px we have both lobes pointing along the positive and negative axis, x-axis, right? The positive side and the negative side, or the positive, or the plus phase and the negative phase. All right. This is the py. The y is basically going into the slide, and so if we're looking at it from that side, we're not going to see the actual shape. We're basically going to see the outer parts of the orbitals, and then, but of course, we have along the positive y-axis and along the negative y-axis, we have 2 different lobes. They are of equal. They show equal electron density distribution, or equal probability of finding the electron, but in different, but described by different phases of the wave function. All right, and here we have the z along the z-axis, more or less the same thing. Now, in this case, we're showing 2px, 2py, and 2pz orbitals. The 2 again is based on the principal quantum number n, and the fact that all orbitals have the same value, right, means that the orbitals are of the same energy. They have the same shape, they have the same size, and the electrons that are in them have the same energy, right? And we describe these orbitals, these 3 p orbitals, as being degenerate. Going back to the idea of ML, where ML describes the orientation, we have a value of 0, -1, and +1. The Z is the one that is defined by 0. Well, let's see here, which one is Z? Well, we could choose basically which one. It doesn't really matter which one. But we're basically showing that each of them have 3 different values. One is -1, one is 0, and one is +1, telling us that we have their orientations in space are all different. Okay. What about d orbitals? Now, we're not going to go through looking at the wave functions of the d orbitals, the mathematical wave functions of the d orbitals. But for d orbitals, we're talking about L is equal to 2, ML is equal to -2, -1, 0, 1, and 2. Alright? This tells us that there are 5 d orbitals. And if we were to look at the mathematical wave functions, the wave functions, and if we were to depict those wave functions graphically, this is what they would look like. And you see that there are lobes that are either along axes or in between axes. Now, what is peculiar about, or particular about the d orbitals, is that they have the angular wave function basically defines them as having 2 angular nodes. Alright, let us look at these examples up here. We have 3 up here called dxy, dyz, and dxz. They have, first of all, they have 2 angular nodes, but before I get into the angular nodes, they have, they look almost like 2 sets of p orbitals basically crossing. That's not quite what it is, but that's a nice way of looking at it, where you have a pair of lobes, right, pointing along in one direction, and another pair of lobes basically perpendicular to the other pair of lobes. Alright, now in the case of the dxy, we have the one pair of lobes in between the x and y planes, right? This is x, this is y, and this is x. We have a pair of lobes in between the x and y plane, and we have another pair of lobes in between the x and y planes. Alright, so all the lobes of the orbitals are in between x, y planes. Now, there are 2 angular nodes, one angular node along the x plane or the x-axis, and another angular node along the y-axis, and they're basically vertical, right? So they pass, or both of them pass through the z-axis, and they're perpendicular to each other. So these 2 angular nodes again indicate to us that there is 0 electron density in between the lobes, right? And also 0 electron density where the lobes, or rather where the nodes intersect at the nucleus. Again, similar to the p orbital, where we have we have the lobes, right? But in between the lobes we have a nodal plane. We have a similar case in the d orbitals, except that you have 2 lobes, or sorry, 2 nodes along 2 different axes that are perpendicular to each other, which separate the electron densities, or the orbital lobes themselves, which tell us that in between the lobes there is 0 electron density, and also where the nodes intersect there is 0 electron density. Or in other words, at the nucleus for electrons in a d orbital there are no electrons. For the dyz, the lobes basically point in between the YZ axes, alright? The YZ axes, and the same thing for the DXZ, the lobes point between the XZ axes. Now notice that for both pairs of lobes, one pair of lobes have one shade and the other pair of lobes have another shade. This basically is indicating to us or representing the fact that for a pair of lobe, these lobes have one phase and these lobes have another phase, a positive phase and a negative phase. These pair of lobes have one phase and another phase. Alright? Now, then there are two other d orbitals called the dx squared minus y squared orbital and the dz squared orbital. The dx squared y squared orbitals are different from the xy, yz, and zx in the sense that the lobes point along the x and the y lobes, right? In these examples here, the lobes point between axes, but in the x squared y squared, the lobes point along the designated axes. X squared y squared, x, right, and y. Okay? And again, we have two planar nodes. Let's see. The nodes are essentially in between the lobes. All right. They again are they're vertical, pointing along the z-axis vertically, but they are in between the xy and the xy planes. That is to say, one is in between this one and one is in between these two here. We'll look at it a little on the other slide. And then the dz square basically has two lobes pointing along the z-axis and a ring along the xy axis. So here we have these two diagrams here of these orbitals showing the lobes and their respective nodes. For the x squared y squared, we have the lobes pointing along one set of lobes, the positive lobe, if you may, pointing along the x, and the negative lobe pointing along the y. And then we have one nodal plane that is in between this xy here, and then the other nodal plane that is perpendicular to it. Alright, again, because we have a nodal plane passing through the middle, it tells us that we do not have any electron density at the center, which is the nucleus, effectively. And then the dz squared, the nodal planes, or the nodes, I should say, do not form planes, but they form cones. Alright? So the surface of the cone is a region of zero electron density. Alright? Yes, we're pointing along the z-axis, but where we have the surface of the cones, we have zero electron density. And what that does is that it's sort of, the reason why we have a ring along the xy axes is because the surfaces of the nodal cones basically force electron density along the xy axis. Alright, and those are the x squared, y squared, z squared orbitals. Now, going back to all five of them, because let's say, for example, we're talking about n is equal to 3, then we're saying that these are all d orbitals, 3D orbitals, sorry. 3dx, 3dy, sorry, 3dxy, 3dyz, 3dxz, 3d x squared y squared, 3d z squared. Because they all have the same principal quantum number, these orbitals are degenerate. But you will find out that they're not entirely degenerate. In fact, you have two sets of degenerate orbitals. These here are of the same energy, and these here are of a different energy. But we don't want for you to get into all of that right here, right now. Alright? Okay, so this is basically our look at the Schrodinger atomic model, which basically defines the structure of the atom in terms of orbitals, right? Regions of space within which the electron is moving in, defined by a specific wave function, dependent on the principal quantum number n initially, and other quantum numbers, the angular momentum quantum number and the magnetic quantum number, and that these electrons, the probability of finding the electron within the region of space essentially defines essentially the orbital, or the orbitals allow us to be able to define or get an idea, or get an idea of the probability of locating the electron within that specific region of space. And so in summary of what we've learned is that the Schrodinger model describes the wave motion of an electron moving within a confined space as a wave function, that the wave function is decomposed into the radial and angular components which describe the region of space that the electron is moving in. The square of the wave function is equal to the electron probability density, or the probability of finding the electron within a specified region of space, and that this specified region of space defines what we describe as an orbital, and these orbitals are different as described by the quantum numbers n, l, and ml, okay, which effectively define or describe or tell us the energy, the shape, and orientation of these orbitals. And so for the next session, we want to review section 2.5 in the textbook, read ahead section 2.6, where we're going to be looking at the electronic configuration of hydrogen, and then of many electron atoms, or atoms that have more than one electron. We're basically going to use the idea of what we know about the shapes of orbitals, and basically assign electrons to these orbitals, which basically allow us to define or describe the electronic configuration of atoms. And then, to explore the concept, I wanted to look at worked example 2.8. I don't know why I have worked example 2.8 twice, but worked example 2.8, let's see, and another worked example, 2.9, which essentially looks at atomic orbitals and radial wave functions, and then explore the concept even further by looking at box 2.4 and box 2.5, which basically looks at p orbitals and d orbitals. Okay, so till next time,